Alright, so let's get started. Today we are going to be talking about arithmetic expression optimizations and stack allocation optimizations. So in our last lecture we added support for pointers, and it did require a pretty big overhaul of how we handled our number class and our LOVM value class. But as a result, we now get, n-depth pointers, which is really cool. ACWJ doesn't do that for a while, so it's neat. Let's talk a little bit about optimizations. Optimizations are just modifications that the compiler makes to parsed ASTs or to directly generated LLVM with the aim to keep the same behavior at runtime, but just make it faster or reduce the binary size typically. And there are like security optimizations, I guess you could call them optimizations, where the goal isn't to make it faster or reduce binary size, but just to make it more secure and make sure that fewer attacks can be made. The ones that deal with ASTs are obviously going to be recursive most of the time, but a bunch of times we can apply optimizations as soon as we parse an AST, like in a for statement or something. We are probably going to look at those optimizations in a later lecture, but one of the optimizations we're going to look at today is going to be a recursive AST traversal. And because we have a recursive AST traversal, we are going to be subject to depth first traversal complexity, which is O of the number of vertices times the number of edges in the tree. We are going to see that it greatly increases the compile time duration when we compile large files. However, there are some hacks that we can do to get around that. That duration increase is the reason why Clang and GCC, their default optimization levels are 0, which means it's not going to do anything different than you would expect. We are going to leave it on, and you'll see why in a second. So the goal. I've written this script that I'll show in just a second, and it generates a random file for echo to compile. It contains 500 print statements. Each of them has 5 to 10 binary arithmetic operations, which means that it's got between 6 and 11 integer constants. And our goal is to minimize the output of the LLVM generated for this file. So I'll show you the script. Right here, yeah. So all we're doing is this n gets set to 500 when I run the PyTest script. We've got some set of operations. I took out division because it'll throw division by 0 errors, I don't want to write the logic to test whether or not there's going to be a division by 0 error. So I'm just going to leave division out. It's not a huge deal. Division acts close enough to the other operators that I'm not concerned. We can, in the future, if we really want to, we can write a specific division test. But for optimizing, we could just use pluses and stars for all I care. But anyways, so we've got this set of operations. We've got this sub function called get sub expression, where we choose a random one of the operators. We pick a random value for our left and our right operands, unless a sub expression gets passed in. And the only reason I did this is because when I was first writing the tests, I was concerned about left associativity versus right associativity of the operators, if you guys are familiar with that. Do you know what associativity is? Basically, no, I can't summarize it well enough. Operator associativity. Basically, the result of an operator kind of like sticks left or right to the rest of the expression. But the reason why it didn't matter in the end is because those four basic operators are all left associative. But that's precedence, associativity. Yeah, left to right associativity, that's what all four of the basic ones have. I don't know. Long story short, you don't have to worry about it. Not yet. Other operators are going to have right associativity. But
I see. Prefix, increment, and decrement.
And exponent is usually right associative also.
That makes sense.
Yeah. But, yeah, so I was worried about associativity, so I ended up passing in sub-expressions, but it doesn't matter. It's all good. So we just generate a bunch of sub-expressions, stick them together, stick a print statement in front of them, and then we're going to add a comment after that line to just show what it should be, what the value of it should be. And then we also have this expected output. That's what we're going to use in PyTest. Wrap it with an int main, write it out to a file, and then return the expected output to our PyTest script. And I'll show you what one of these files looks like. Okay, examples, arith_test. Yeah. So that's what we got. We have this big file, bunch of arithmetic expressions. 500 is a good number to test with.
How does it compare the evaluated expression against the predicted result? Now, how does your test script compare the evaluated expression against the predicted result?
Because it evaluates the expression.
No, I'm just saying, how does it...
Oh, well, it runs through our normal PyTest stuff.
Yeah.
So I just give it the name of the generated file, and this returns the output of the script, or the expected output based on Python's eval function.
I say just call the tester function.
Yeah. So, yeah, that's the goal. Is we want to compile that. We want to get some LVM out of it, and we want to minimize the amount of lines that LVM generates. So you'll notice I'm not saying let's minimize the runtime of the program, because Clang is going to perform optimizations on its own anyways, and we can't stop it from doing that. So this is less about teaching you how to write LLVM generation optimizations and more about the concept of optimizations and compilers as a whole. So this will not change our runtime, but it is going to make our LLVM files smaller, which is good for us because that makes it easier to debug, right? So this is the plan. We are going to implement 2 optimizations, and we are going to slightly update how we deal with LLVM value constants so that we can minimize our generated code. So the first optimization is called arithmetic expression folding. You brought that up earlier this semester. The other one we're going to do is stack allocation reduction, and then we're adding a new LLVM value type constant so that we can detect any missed optimizations that our optimizer might have forgotten about, or I don't know. Recursive descent is hard, so adding last minute checks dropped the total number for me of generated code. So with arithmetic expression folding, if we've got this print statement, 1 + 2 - 3 × 4 / 5, there's really no reason why that should be computed at runtime. That expression is going to have the same value today as it does tomorrow, as it does a million years from now. So we really should just fold it down into its true value, right? It doesn't depend on any external variables. We don't have any operator overloading or anything yet, so we should just fold it down into its value, which is 1. If you plug it into Python, you'll see it's 1. And that way we won't waste any time at runtime computing that, or we won't generate the code to compute it. And it also works for sub-expressions as well. We've got print 1 × 2 + x - 4 / 5. You don't need to compute 1 × 2 and that should be 4 divided by 5. So it should just be print 2 plus x minus 0, because integer division, 4 divided by 5 is 0. So these are the 3 sets of folding rules that we're going to apply. The first one is that any node that has an operation and 2 integer constants, just compute its value. Super easy, right? We've got a set of 0 rules. So if we have x plus 0, we know that's always going to be x. We know that x times 0 is always going to be 0. We can catch any accidental divide by 0 errors at compile time, which is nice. And then we've got a rule for double operations. So there's, for addition, multiplication, subtraction, whatever, any expression that has 3 constants and 2 of the same operation in a row can be simplified out. And so we'll... Yeah. So let's look at those rules.
What about like multiplying by 1? Do you fold that?
I should do that, but I didn't do that. Yeah.
Sounds fun.
Well, I mean, it gets handled by the 2 constant.
Like x times 1.
X times 1, no. But I should add that in. You're right. Dot pi. All right, so we have this big, where is it? Optimize AST function right here. I'm just going to open this file up so we don't have to. So we've got this optimize AST function, and it is going to get called whenever we have that parse binary expression function. It's the recursive Pratt parsing and all that. So I wrote a wrapper around it. One, so that we don't have to pass in a 0 every time as the previous token precedence, and also so that optimize AST gets called every single time you parse an expression.
We have a new argument for optimization?
What do you mean?
Wait, we have an argument for optimization?
Well, yeah, we have to give it a node to optimize, right?
No, I mean a command line argument.
Yeah. So I just added this. I was about to say. It's got 3 levels: 0, 1, and 2. 0 is what we're used to. It won't generate any different code than what we've had up to this point. For 1, it is going to only do 1 pass of the. I'll explain this loop in a second, but it's basically going to do 1 pass of everything. And then optimization level 2 is going to recursively descend and touch every single node in the AST. So what we do here is we've got this deep copy of our root before we do any optimizations. We're going to call it before opt. We've got another deep copy called opt pass. Opt pass is just going to be it's going to be the output of every incremental optimization that we do. Because we're doing a depth first search, we're obviously gonna depth first, traverse every single branch in the tree. And then the actual optimization loop is right here. So we're gonna say, as long as this root has children, so that's our condition, because you can't really optimize a single node on its own, right? We don't have anything to optimize like that. As long as we've got children, we're going to update our before optimization. We are going to pass it through each of the 3 optimizations one by one. Output of the previous optimization goes as the input of the next one. And then the only time we're going to break, besides if we don't have any children, is if the output of all 3 optimizations is identical to the input to all 3 optimizations. So that means we haven't changed anything in our AST, so why would we run it through the optimizations again, right? Or if we only want to do 1 pass. So let's look at 2 constant. Right here. So fairly simple. I have these helper functions that just make sure that this node exists and its type is a literal value. So notice I didn't do any kind of checking before I passed into any of these optimizations, just because this should be kind of a wrapper function for performing each of those individually. So each function is going to do its own checking for whether or not the optimization can be performed. But we're going to say, if both of our nodes aren't constants, just return the root. Otherwise, we are going to, compare the type of our root to each of the four operations that we've already used before, and then we're going to compute their value in Python with the appropriate operation, and then we're going to construct an AST node, type integer literal, and with the value that we computed. Does that make sense?
Is there a condition? Is there any condition where you don't have root less than root right?
Oh yeah, inside of isConst, it makes sure that this exists. I'll just show you. It's right here. Root has to not be none.
Yes.
So if root does not have children here, or if it only has a left or it only has a right, then this condition will fail, and it'll return root.
So why is it in the if state? Why is it in the if checks?
Huh?
Why is it in the if elif block after that, I'm asking?
Why is what? Oh, because of my linter.
Why about your linter?
So technically, there's nothing saying that between this block of code and this block of code that root.left or root.right didn't get modified. It's possible they did get modified because Python will let you do that. It'll let you run things in parallel, and it'll let you, maybe this function, so maybe this check right here could modify root some way, or this function right here could modify root some way. So the linter doesn't know whether or not that's true or not, so it's going to make you say yes and root.left and root.right.
Oh.
So just appeasing the linter. I like not having errors and stuff, so I'll do it once. Same thing right here, kind of. Really, we're never going to have two integer constant children if there's not a plus, minus, star, or slash.
But you gotta have a return.
Yeah. So, yep, that's what we got. So that's our two constant optimization. I think it's fairly straightforward. So now we can look at the zero optimization rules. So these are the rules that we're applying. X plus 0 equals x commutative, which means that 0 plus x also equals x, right? X minus 0 equals x. 0 minus x equals negative x. X times 0 is 0 commutative. 0 divided by x is 0. And x divided by 0 throws an error, right? So this one's a bit more complicated, but I just constructed this 0 AST node because there's a few places I have to return it. But we get the non-zero child of one of the two. If there's no non-zero child, then we're just going to return, and we don't have to do this optimization. But if we've got a plus, then we can just return whatever the non-zero is, right?
Wait, what was that? What was the return you looked for?
This is when the non-zero child, so this is basically setting non-zero child to either root.left or root.right guaranteed. But if what we set to the non-zero child is a 0 AST node, then we just need to get out of here because this is not the optimization for us. It means that for whatever reason we've got two zeros or something, and so let's just ignore that. We don't want to deal with 0 over 0. That just adds more complexity. So that'll be handled by toConstant. We'll let them worry about that. This is mostly concerned about one node is 0 and one node is something else, right? So yeah, if we've got a plus, it's commutative. We can just return whatever the non-zero child is. If we have a minus, if the left child is the non-zero child, so if you've got minus and you've got left and you've got right, that means left minus right. Right minus left would be a different operation, right? So if we're saying the left is the non-zero child, that's x minus 0. So we can just return x, right? Otherwise, if we have a root that left, this is just linter appeasement again. We are going to negate its value and then just return it. And then, this never happens, basically, but we want to appease the linter. So, next we've got our multiplication. Same thing as the plus, except this time we are going to return a 0 node, right? And then for our division, if the root dot right is the non-zero child, then we're going to return 0, because that's 0 over x.
Otherwise, we return a brand new error.
This one's built into Python. Zero division error. It's built in. So
First time using it here, though.
that's true, yes. And so we'll just say you've got to divide by 0 as the line number. So that's our 0 optimization. Does that one make sense? Okay. And you're right, we can add a 1 optimization. We probably should do that for multiplication and division by 1. Double opt. Yeah, so this is those double operations I was talking about before. So something like this might seem trivial, but I don't think I did it here, but I'm planning to do it. You can, because addition is associative and commutative, which means that you can switch all of these symbols around in any order and the value is always the same. You can switch out the order of your AST nodes, because if you've got plus, you've got x, and you've got plus, you've got y, z.
Yeah.
If these two are constants, then you can't directly optimize that. But because addition is associative and commutative, you can swap x and z. It's the same, but now you've got two constants down here, which means you can automatically optimize that, and you turn this into plus z x plus y. So that's just a nice little optimization that we want to do. And so there's similar rules for multiplication and also subtraction and division, but the issue is you have to invert the second operation. So that's what we're doing here. Don't worry about all this. I don't remember what was going on there, but it needed to happen. It's basically just saying for example, in this first example, we're just going to say this is the target node, this is the non-target node. Don't worry about the distinction. Just know that the target one is the one we want to switch around and optimize and stuff. So if we've got a plus or a star, we are going to pass through this new AST node. We're going to pass it through optimize AST. And we are going to give it the type of our operation. We are going to give it the non-target, which is this, and then target.left, which is going to be this. So that's x and z, like before. So we're making a new AST node with x and z in it. We're passing it through optimize AST, which is our big wrapper function, right? And we're hoping that's going to optimize it down into x plus. Okay, swapping out x and y in this example. I guess I got it backwards. But yeah, doing the same thing that we have here. We're hoping that we get an optimized AST node that's smaller than the child that we had before. And so now we're just going to return an AST node with that optimized left child and then the other target child. right? And basically the same thing is happening here. Create an AST node, invert the operation, like we said right here. Give it the non-target, which I guess in this example is this thing, and target.write, which is this thing. And then we are going to return a new AST node with our optimized right child and the original left child. So that one's more wishy-washy, but it does work, and that's good, and we like that. So is everyone comfortable with the arithmetic optimizations that we've done so far? Are you comfortable with them?
Yeah, I'm still lost in the latest one, but that's about it.
Okay. Well, I mean, at least I think the math is straightforward. You've got x minus y minus z. In our language, it becomes that because that's how we're parsing stuff. Or no, I think we're parsing it. I think we're parsing it like that, and then you distribute the subtraction, and so you get x minus y plus z. I don't know. I mean, I think the math at least seems straightforward. But yeah, if you do enough examples, I think you'll be able to see it just fine.
Yeah, I see where we're going with this.
Okay. Well, that is all we're doing here. Those are the 3 arithmetic rules that we added in.
Successful optimization.
There are plenty more that we can add, but honestly, these do, I'd say, 80% of the work. Eventually, we'll have, or I don't know if we're even going to get to that this semester. We might in the future do function output guessing. And so that's something that a lot of compilers will do, is they'll guess the output of your function. Or some will try to find patterns. So it'll say like, oh, I've noticed that if you give an even number to this function, it's always going to return something in the form of this. And if you give it an odd number, then it's always going to return something in the form of this. And so it'll be able to use that information to do optimizations on its own.
At runtime or?
Compile time.
How does it know what's passed to the function
It
in an actual runtime scenario?
It has to be a sufficiently simple function. So primarily arithmetic, maybe some looping, but definitely no pointers. The moment you use pointers or heap memory or anything, it's all out the window, and you don't know what's going to happen. So yeah, the moment you use heap stuff, you lose a lot of optimization.
You get to do runtime stuff.
Exactly. So stack allocation reduction, that's the next optimization we talked about. The way we've been doing things for a while, and this is pulled directly from the LLVM for that big 500-line file, is we'll allocate 2 spaces. This is for one operation. Allocate 2 spaces. We store an integer into one of them. We store an integer to the other one. We load their values into new registers, and then we add them together.
Why?
We did it because we wanted to learn about LLVM pointers, and we wanted to write an interesting and complex compiler. But now that we've done that, and we know better, we should just stick it into one line that says add 03. And we're obviously ignoring that previous optimization we did. This is just an example. But yeah, so we want to apply this. And let me show you all the stuff that I did to deal with that. So let's see, what did I do in translate.py? Okay, so the first thing that I did was, this is in our determine binary expression stack allocation function. I should expand this. So this is inside of our recursive call. if we see that our root is an integer literal or an identifier, that's when we originally built our stack entry and did whatever, and we were good. And now we're saying, as long as the optimization level isn't 0 and we're looking at an integer literal, do not make an LVM stack entry, because constants don't need to have space on the stack allocated for them. We can just plug them into our own expressions, right? So in the terminal node, so this is where it gets different. Originally, we would store a constant into a new register, right? Now what we're going to say is, as long as the optimization isn't 0, we are going to create this new LVM value type constant. We are going to give it the value of the token, that we computed however we did, and we're going to give it a number type. And so we've skipped any LVM generation. We've just said, don't worry about that. Here's an LVM value. It's got the number you want inside of it. And we can see how that gets used inside of lvm.py. It gets used in a bunch of places. So what I've basically done is I've short-circuited every single place where we maybe could have dealt with a register that has a constant value in it. So example, for the int resize function, I'm just going to say that we're going to make sure that the int value fits into whatever the maximum value of this output number type is. We're not going to worry about resizing or anything. We're just going to truncate if we need to, but otherwise we know it's going to fit. If it's an extension, a 0 extension, we know that our current number is going to fit into the new type, right? If it's a truncation, we truncate, but that's fine. So short circuit, don't generate any LVM for that. We're done. Here's one. Basically anywhere we used a % sign to represent a virtual register, I've now updated it to say only if that's a register. Otherwise, we just want to spit out an exact number. So in our add example, we had add no signed wrap I32. Originally we'd have like %1, %2, because those are virtual registers. And now we want to say 3, 4.
This should help. I was figuring out how to add a left shift. I was figuring out how to add bit shifts.
It could help. I don't know if it'll make any difference, but so that's what we're doing right here. The int value, if it's an LVM constant, is the actual value of the constant, and if it's a register, it's the register number. So we use those fields interchangeably. In all of our, so this happens in all of our arithmetic expressions. It happens in our comparison expression. So when we're storing a global, we're only going to ensure that our register is loaded if it's actually a register. And then otherwise we are going to say, all this only happens if we're looking at a register. And this is what had been happening before. We haven't changed any of this behavior. Otherwise, if we've got a constant, we'll just say store, give it the number type. This is just the value. There's no % there, straight into our global variable. So now we can say store I32 5, at Bob, or whatever we call our variable names. Okay. LVM stack allocation. I think I just did this for safety, because if we try to generate, this isn't stack allocation. This is print it. Okay. Yeah, print it. Now we can directly print constants because that's allowed. You can pass constants into functions and stuff instead of virtual registers. So that's what we're doing right here. LVM return, same exact thing. We can return constant values. We've already seen that. We've been doing it for our main function, right? And bam, that's it. That encompasses all of our stack optimizations. There is one more, and I feel like, did I not cover? Integer literal. Oh, it's because I pushed after I loaded this page.
Oh.
Wait, really? Is it? Let me pull up the code. Maybe I didn't push. I thought I did. Oh, okay. Never mind. I guess I found some way to avoid that. Anyways, so let's look at the example, or let's look at the output. So we can do Python, or let's, go to our echo cat. I'm going to remove all those LVM files. Big old arithmetic file. It's got all the stuff we want. So let's do scripts run, examples, arith test. We're going to say no optimizations because the default is level 1. And let's call it arith test optimization 0.ll. Oh, and also let's time it. Let's see how long it takes to actually compile. Okay. Okay, 5.5 seconds. Let's count the number of lines. So WC is a word count tool. -L means count the lines. Let's count how many lines are in an unoptimized arithmetic test. 18,820. That's a whole lot. Let's do the same thing. Let's give it optimization level 1. Let's see the difference. Eight seconds, and now we only have 524 lines in the entire file. We can do this for optimization level 2. It takes 18 seconds, and it's also 524 lines. So optimization level 2 doesn't do anything for us right now. It will in the future when we want to do a more in-depth traversal of our tree, but right now it doesn't do anything special. But that is a really worthwhile optimization in my opinion. I mean,
10 more seconds for optimization level 2. Should it only go through like one more pass through the tree?
no, because optimization level 1 does one single pass of, it's going to go through less. Optimization level 2 is going to touch every single node of the tree. Optimization level 1 does not. I think so. I should trace this through a debugger or something, but optimization level 2 is going to just do more in-depth touching every single node, seeing if it has anything to do.
Okay. I thought like optimization level 2 went through the optimization loop on the whole tree.
The loop is only going to occur one time for level 1.
Would it only have to occur 2 times for level 2, if I'm understanding correctly?
Unless, well, it's going to go until the output of the optimizations doesn't match, or does match the input of the optimizations.
Mm-hmm.
So if I ran those 3 optimizations one time, and I got a different output, I'm going to loop again. If I did it again and I got a different output, I'm going to loop again. Because there's the possibility that they transform the AST in a way that, does allow for a different change in the next round of optimizations.
Okay, but you said they both had 524, right?
Correct. Well, and I'll show you why they both have 524. 0, 1. It's only print statements.
Mm-hmm.
We've broken down all of the stuff into print statements. that's why it can't be optimized any further.
Can I see what the first one looks like?
Yes.
Yep.
Bunch of loads, bunch of stores, bunch of arithmetic. It's so much that I can't scroll up any higher on my terminal. So definitely worth it. And we said it was like 8.5 over 5.5. So we add 50% of our compile time, but we reduce, it was like 18,800 over 524. 35x reduction in the amount of generated code. Crazy worth it, in my opinion. I mean, all right, no.
How long does claim take to go through like the 18,000 lines?
Um,
Convert it to,
That's a good question.
and compared to like the other one.
Claim arith test 0. 0.0246 seconds. It's probably going to be a very minimal difference. Oh, 0.165.
Pretty good actually.
Yeah. So, and you imagine that if we continue to scale this up, that difference does get bigger over time. So that's a significant optimization in my opinion. I think it was worth doing this. But yeah, so that's all I've got for y'all today. Are there any questions? No? All right.